introduction to crystallography. Now, as a slight disclaimer, of course, we could give many lectures on the field of crystallography alone, but I'm just going to cover some of the main basics to make sure that we're all talking the same language so that we're able to cover some of the things that we need to later. So this is a very basic introduction, and I won't go into huge amounts of depth. If you want, there are more resources available and I can point you in the direction of those resources. But for now, this is just a very brief introduction, as I say, a whistle-stop tour to crystallography to make sure we're on the same page. So let's start here with a picture of a wallpaper pattern. So as we can see, this wallpaper has a nice regular structure to it. It's periodic and is repeating out in all different directions. It has a so-called translational periodicity to it. If I take it and displace it in a certain direction, I would end up with the same pattern. So what I could do is I could locate points on this structure or on this wallpaper that look identical. Any one of those dots that I've put on there, if you were to sit on that dot and look around you, the structure looks exactly identical. The pattern is identical. So this defines something that we call a lattice. What we've defined here are a series of lattice points, which are all identical, and we have defined a two-dimensional lattice of those points where the structure is identical. So you can see that I've got this periodic structure, this translational periodicity that repeats out in all directions. So let me just go back and flick back and forward between the two, and you can see I've defined these points that are all the same, and this defines my lattice points and my lattice structure here. Now, if I've got this lattice, what I could do is mathematically define this lattice by some vectors on it. So what I've got here is I've got a picture of some vectors. Just focus in on this one to begin with. I've got a picture of a little rhombus here that I've defined by vectors A and B. And starting from any lattice point, I could have some combination of those A and B vectors that would lead me to any other lattice point within the structure. So what I could do is write mathematically an equation up here, R equals UA plus VB, where R would give me any vector between those lattice points within the structure. And this is what mathematically describes this structure. If I have a lattice, then I should be able to write an equation like this, made up of lattice vectors, where I can go with some combination of those things. Now, it's worth noting that this is not necessarily a unique combination of lattice vectors, and I could define any number of lattice vectors that could define this lattice. So over here I've got a different set of lattice vectors that I'm defining that would also define my lattice. Up here I've got a different set of lattice vectors that also defines that lattice, where basically I'd go from this point to this point and then over to this point and so on and so forth. Now, each of these, you can see, we could also think of it as defining, between these lattice vectors, we've defined a small cell, a so-called unit cell, which I could take and move around and so build up that entire structure. And going back to my pitch here, you can imagine if I took one of these small like rhombuses here and just repeated it in all directions, I would eventually form that entire pattern that I've got here. And I could do that with any one of these cells here. I could also do the same thing with this cell over here, but it's worth noting that this cell is slightly different because this cell has a lattice point within it, whereas these three cells shown on the left only have lattice points on the corners. This one has a lattice point within that cell. And the difference between these are the ones on the left are so-called primitive because they only contain one lattice point, whereas these ones over here are not primitive because we have more than one lattice point. Now, you might be looking at this cell and going, well, how have I only got one lattice point within this? Well, if you think about each of those lattice points on the corners here, only part of them is actually within the cell. There's only a fraction of it within the cell. And if I added up those fractions, I'd see that there is only one lattice point. And actually, if you just translate it ever so slightly, you could be able to convince yourself of that. So if I go to this unit cell here, if I were to draw it between the lattice points here, you might not be convinced that it only contained one lattice point. But if I were to just translate it ever so slightly, so it didn't actually sit on the lattice points but slightly off the lattice points, you can see that there is only one lattice point within that cell. So these three here define primitive cells, and these two over here define non-primitive cells. And the key thing, or one key thing to note here, is we can use different cells in order to define the same lattice. So whenever we have a lattice, it's really important to understand what the lattice vectors are and what unit cell we're using in order to define it. So that is the first thing to say about lattices and unit cells. The other thing to note is that we could have the same lattice but ultimately build different structures. For example, I've got this wallpaper pattern that I had here, and I said that it was defined by this lattice. But this wallpaper pattern would in fact be defined by the same lattice. If I flick back and forward between them, you can see that they've got the same lattice, but they've got overall different structures. And that's because I've put different so-called motifs on those same lattices. So in the first case, I have this sort of floral ferny type motif that I put on this lattice and build this wallpaper. And in the second one, I've put Snoopy on each of these lattice points, and that's defined this slightly different wallpaper. So when I'm building this overall structure, not only do I need to define my lattice, but I need to define the structural motif that I put on those lattice points. And this is going to become very important when we consider crystallography and when we consider our real material structures that go into it. So generally, anything that has this sort of translational periodicity, we can describe by this lattice. And we not only can do this in 2 dimensions, but we can in fact do the same thing in 3 dimensions as well. So rather than just having 2 lattice parameters A and B, we have 3 lattice vectors A, B and C shown here. And I could define the vector between any 2 lattice points by this equation shown at the bottom here. It's worth just noting here on this diagram that I've drawn on some angles alpha, beta and gamma here between the different vectors. And there is a standard convention in crystallography as to how these are labelled. So the standard convention is that the angle between 2 vectors is given by the Greek letter that completes the set. So if I have the angle between alpha and A and B, for example, the missing vector in that set would be the C vector. And so if I think of alpha, beta, gamma as being sort of corresponding to A, B and C, I'm missing C, so the angle between them is the gamma angle here. Similarly, between, for example, vectors B and C, the missing vector in that set is the A vector, and so the angle between them is going to be defined as alpha. So this describes my 3D unit cells from which I could build up some sort of translationally periodic structure. And it turns out that if we think about it, there are only a limited number of ways that I could define unit cells, certain shapes that unit cells would have within them. And in fact, any unit cell that I have in 3 dimensions is going to be one of 7 crystal systems. So what I can think about is these vectors and the angles between them and various restrictions that I could put on them. So for example, if I were in a cubic structure, what that means is I've got A equal to B equal to C, so all of these vectors are the same length, and the angles between them are all 90 degrees. This is an orthogonal basis set. And it turns out there are only 7 different shapes of cell that I could have that would be translationally periodic in 3 dimensions, and they have these. So cubic, we've got these orthogonal axes, A equal to B equal to C. Let's move next to tetragonal. This is where I take my cubic structure, and if I were to pull it in one direction, that would make one axis a slightly different length, but I've maintained all the 90-degree angles. And then if I were to pull it in another direction, I would get the orthorhombic structure, where A does not equal B, does not equal C, but alpha, beta, and gamma are still all equal to 90 degrees. So I can draw these structures that I'm showing here. So I've got my cubic, tetragonal, orthorhombic, hexagonal, triclinic, monoclinic, and rhombohedral or trigonal. Rhombohedral and trigonal, it turns out, can be defined as similar to each other. It's probably too complicated to go into now, but if you're dealing with those space groups, it might be something that you have to take slight care over. Triclinic is the lowest system, the lowest symmetry system, where alpha A does not equal B, does not equal C, and alpha, beta, and gamma are non-equal and non-90 degree angles. So these are my cells that I have here. So anything that is translationally periodic in 3 dimensions should fit into one of these crystal systems. Now notice here on this diagram what I've said is that these are primitive crystal systems. If you recall, we said that we could have unit cells that were non-primitive as well. And it turns out there are certain types. So if I take the cubic system, there are 3 different cells that I could have. I could have the primitive, I could have a body-centered where I've got one lattice point right in the center of my unit cell. And I've got my face-centered cubic where I've got lattice points on the opposite corners or on the opposite faces of my unit cell. So the primitive only has one lattice point. The body-centered has one shared between the corners and one in the center, so overall has 2 lattice points. And my face-centered cubic has one lattice point on the corners, one on that set of faces, one shared between that set of faces, and one shared between that set of faces. So overall, my face-centered cubic has 3 lattice points associated with it. And it turns out that you can have certain types of crystal system in combination with certain types of centering, and this defines the so-called 14 Bravais lattice systems. So for a cubic, we said we had simple, body-centered, and face-centered. For orthorhombic, we can have simple, face-centered, and body-centered, and we can also have base-centered, where we just have two faces that have an additional lattice point on, shown there. For tetragonal, we can only have simple and body-centered, so primitive and body-centered, as shown there. So these are our 14 Bravais lattices, and all 3D translationally periodic structures could be described with one of these 14 Bravais lattices. Now, there is a reason why we can't have a base-centered cubic structure here, which we'll mention again in a second. But in order to consider that, we need to consider symmetry within the structures as well. If I go back to my wallpaper pattern that I had here, one thing that you might notice that we can say defines this structure is there are mirror planes within this structure. If I were to draw some vertical lines running down between these lattice points here, we could see that I could reflect this pattern from one side to the other. Whereas if I compare that to my Snoopy pattern here, I've got no mirror plane. If I were to try and reflect that structure, Snoopy would end up pointing in the wrong direction. So actually, we're going to have to consider symmetry within these systems as well. And there are lots of different symmetry elements that we could have, and some of them will be more or less familiar to you than others. So for example, we could have an axis of rotation where if I were to take everything and rotate it round, I would end up with the same structure. So here we can see what we've got, what's called a dyad, which is a 2-fold rotation. So if I were to spin everything by 180 degrees around that axis shown there, I would end up with the points shown here. I can have mirror planes within my structure where, as we say, if we reflect everything from one side to the other, we replicate my pattern. It's worth noting I've put a little comma in here to show that basically I flipped the inversion, as we saw with, for example, if I have something that had a handedness to it, right and left-handed, for example, if I were to go through a mirror plane, it would make everything that was right-handed, left-handed, and vice versa. We can have centers of inversion, where basically I take an object and pull it through the center of inversion and go out the other side. There are also some more complicated symmetry elements, things called screw axes and glide planes, which are a combination of a rotation with a translation in the case of a screw axis, or in the case of a glide plane, it's a reflection with a translation as well. These are so-called compound symmetry axes that I have here. And actually, when we defined these unit cells, one thing that we missed out was a minimum symmetry requirement. Because you might be looking at this and saying, well, hang on a minute, triclinic, A does not equal B does not equal C, but alpha equals beta does not equal gamma. Could we define these angles as 90 degrees? Well, actually, what it turns out is there are certain symmetry requirements that we have in order to say something belongs to one of those crystal systems as well. So, for example, if we take a tetragonal crystal system, we have to have one tetrad, one 4-fold rotation axis within the system in order to describe something as tetragonal. So if you think about, for example, a sort of long cuboidal shape, like a wine box shape, and you were to look down it, there'd be a fourfold rotation axis at the end that defines that. Cubic, it actually turns out what defines a cubic system is not the tetrads, but triads. A cubic system has 4 triads that form the body diagonals of the cube. So these are the minimum symmetry requirements in order to have these. But what if we've got our 14 Bravais lattices and our crystal systems as well, and we try to combine it with symmetry elements, it turns out there are actually only certain symmetry elements we can have in combination with each other. Because if we put in a mirror plane and then we try and put in another mirror plane that's, for example, perpendicular to it, that will then restrict certain symmetry that we have within the system. And this is what defines our space groups. And it turns out that a combination of these crystal our unit cells and these symmetry elements, we've only got 230 arrangement or ways that we could possibly do this and still have something that's translationally periodic in 3 dimensions. And this defines our space groups, and you might have seen these before. So for example, here I'm showing a picture of what's called the P21 upon C space group. And we might be able to start to see things that we recognize in this. So P means that it's primitive, 2-1 is a 2-1 screw axis, and C is a C glide plane. And I've got a picture here where we've got certain symmetry. This is my overall unit cell, and we've got certain symmetry elements within it. We've got centers of inversion. We've got screw axes shown here. You can see here that this angle is non-90 degrees. It's got a beta angle that's non-90 degrees, and that therefore means that this system is actually monoclinic. And if I go back and look at my minimum symmetry requirement for a monoclinic is 1 dyad or mirror plane. And in fact, this has a dyad. In fact, it's a screw axis, but that is going to be my minimum symmetry requirement here. And as we say, certain combinations of symmetry elements can go together, and these can become quite complicated. And so these are my space groups that I'm seeing here. So this is a picture of a much more complicated space group. This is the I4 upon MMM space group. This is a tetragonal space group that I'm showing here. And we can see lots of different symmetry elements on here. And so people draw up tables, and there are various tables online showing these space groups that you can look up. But it's worth being aware of these space groups and what they mean and understanding the crystal symmetry of one of these things. Now, what does this mean for our diffraction and things like that, or what we're trying to study? Well, if a material is a crystal, then it will have one of these translationally periodic structures in 3 dimensions. As a slight disclaimer here, the definition of a crystal has changed slightly recently by the International Union of Crystallography to account for quasi-crystals. But in a simplistic way, what we can say is that it's something that shows this periodicity. Now, most crystals that most people will study will show this 3D translational periodicity. If you're going into quasi-crystals, it shows periodicity, but it will be in a higher dimension. But for most of the things that most people will study from day to day with diffraction, we're looking at crystals and something that has that 3-dimensional periodicity to it. And that means that we can describe it with a lattice. It means that we can describe it with a 3D unit cell. And that 3D unit cell will have some sort of space group associated with it that defines the symmetry elements that we observe within it. So it might be something like one of these, like P21 upon C, or something like that. So when people are talking about a particular crystal structure, what they're referring to very often is that something with that translational periodicity, where we're defining it by a unit cell, and that unit cell we can define with one of these space groups that we can look up and tabulate online. And there are various resources that I'll make available, or I'll give links to in some of the notes, links to where you can look up these space groups and look and work out what these crystal structures are and consider these crystal structures for a particular material.